Next, we're going to look at energy and now we're going to look at energy and matter. Energy makes objects move, it makes things stop, and is needed to do work. Did you know there's two types of energy? Potential and kinetic. As the name implies, potential energy is potentially there. It's there, it's available if needed. Kinetic is energy of motion or movement. Okay, the basic definition of energy makes objects move, it makes things stop, and energy is needed to do work. Well, what is work? We do work all day long in our everyday lives. Even just breathing right now is work. You can see the whole list of things here, and I'm sure you can come up with plenty of other things that involve work as well. Each of the following is either potential energy or kinetic energy. Can you figure out which is which? Rollerblading, that's right, that's energy of motion, movement, that's kinetic. A peanut butter and jelly sandwich, just sitting there not doing anything, that would be potential. If you consume that energy, well, we know what happens when you consume energy in calories. We're going to talk more about that in this lecture, but that's potential. Mowing the lawn is kinetic. And gasoline in the gas tank. Notice I'm not saying gasoline being burned, just gasoline in the gas tank, that's potential. Energy is manifested in different forms: heat, work, electrical, and light. You can see all sorts of interesting information here. The units of energy. In the chemistry lab, we're typically going to deal with joules or calories. And don't forget the metric system. I can apply the prefix kilo as well to anything. A kilocalorie, a kilojoule, and just again like in the last lecture, 1 kilo of anything is equal to 1,000 of the base units. A calorie and a joule, you can see the equality there. And then what is the definition of a calorie? Well, it's defined as the amount of energy needed to raise 1 gram of water 1 degree Celsius. Who knew, huh? When I think of calories, I don't know about you, but I think about how many calories are in that Snickers bar. Okay, let's take a look at the example down here. A regular soda typically reports that about 160 calories in a 12-ounce can. Almost all of these are in the form of sugar. How many joules is that equal to? So again, like in the last lecture, we're given 160 calories. That's our given. You can put that over 1 if you'd like to. And we're trying to go from calories into joules. Whatever you're getting rid of, you put on bottom. Whatever you want, you put on top, and I want an answer in joules. So I need to know how many joules is equal to 160 calories. Well, again, think about going between inches and feet. Mathematically, it works the same way. We need an equality. And up here at the top, this one right there, shows that 4.184 joules is equal to 1 calorie. So if you multiply across the top, divide if it's on the bottom, you will see that 160 calories is equal to 669 kilojoules. Oh, wait a minute, that's not what I said. Well, check this out. Calories in food are reported in calories, but they're actually kilocalories. This is indicated by the capital C. So there's a big difference, and I'll put it up here, between a calorie with a capital C and a lowercase c calorie. 1 dietary calorie, as I like to call it, is actually equal to 1,000 true calories, what we know of as a calorie and what was defined up here. So if I am looking for calories, capital C calories, I want to erase this. I want 160 capital C calories. 1 capital C calorie is 1,000 true or lowercase calories. And then, all right, so let's look at this typical energy caloric values for the three food types. So for instance, let me blow this up here. This is a nutritional label for some snack crackers. Whoops, sorry, it's turning on me here. And the calories that you would consume when consuming these, let's say a serving size of 14 crackers, the calories come from fat, carbs, and protein. Okay? Cholesterol, sodium, you'll learn no calories associated with them. So have all the cholesterol and sodium you want. That'll kill you for other reasons. Okay, so fat, carbs, and protein contribute to the calories we would intake when eating these crackers. You can see from my table here, sorry, it's already marked up. You can see from my table here the calories per gram of food, depending on the food type, carb, fat, or protein. So typically we're going to be looking at kilocalories per gram. This means for every 1 gram of carbohydrate, you're consuming 4 kilocalories of energy. Or, I don't like to look at these bigger numbers, but if we wanted to talk about the unit of joule, we could say kilojoules. We could say you would say for every 1 gram of crackers you consume, you're consuming 17 kilojoules of energy just based on those carbs. So for the crackers, we're gonna add up all the energy here in just a second and figure out what the total calories consumed is. Down here, just some other interesting information. Sorry, my table's all marked up a little bit here. But just from common foods and the energies associated with them. You'll note some things have no carbs, some things have no fat, and almost everything has at least some kind of protein associated with it. But each one, carbs, fat, and protein, all tie to a particular amount of calories, and then you add them up to look at your total caloric intake for a food. Okay, the amount of energy you need each day depends on your age, your gender, and most importantly, I think, your level of physical activity. If you consume more food than the energy you use burning it off, well, guess what? You're going to gain weight. If, on the other hand, your caloric intake is less than your caloric output, or burning off calories, you will lose weight. Down here you can see just some basic energy expended for doing different activities for an hour. So if you ran for 1 hour, you would burn off 3,100 kilojoules, or 750 kilocalories. You'd probably burn off those crackers, I bet. My favorite activity, sleeping. Guess what? It doesn't burn off much, but hey, at least it burns something. All right, how many calories would you consume if you ate those 14 crackers? 14 crackers, that's the serving size for this particular food substance. Now, here's what you got to look at. There's 4 grams of fat, 19 grams of carbs, and 2 grams of protein in these crackers. As I said, there's also salt and cholesterol, but they have no caloric intake or caloric quantity tied to them. So basically, we need to use this table, we need to use this table from earlier, and the fact that if we're going to do this in kilocalories, as you'll see we will, we're going to need to use the 4 kilocalories per every gram of cracker consumed, the 9 kilocalories per every gram of cracker consumed, and the 4 kilocalories per every gram of cracker consumed. Okay, so there's 4 grams of fat in this serving size of cracker. 4 times the energy caloric value for fat, 9. 4 times 9, because the grams will cancel. Based on the fat, you're consuming 36 kilocalories of energy. Sodium, yay. No energy associated with sodium. So consume all you'd like. It will kill you for other reasons. Carbs. In this 1 serving size of cracker, there's 19 grams of carbs. There's a lot of carbs in crackers. Each gram of carbohydrate consumed is tied to 4 kilocalories, so grams on top, grams on bottom cancel. You multiply 19 by 4 and you get 76 kilocalories of energy just for the carbohydrates. And then last but not least, I've got protein, 2 grams of protein in this serving size of cracker, and protein, similar to carb, is 4 kilocalories per gram consumed. So grams cancels, 2 times 4, 8 kilocalories from the protein. Add it all up, and if you consume this 1 serving size, 14 crackers, of these particular crackers at least, you're going to consume 120 kilocalories of energy. All right, how do we actually measure calories in food? No, we didn't just feed some guy, some guinea pig, who, let's call him, who was willing to eat a bunch of food and then measure how much weight he gained. Because remember, even breathing is going to be burning off food. Well, so we've got this device called a calorimeter, and it's used to measure heat transfer. Well, what's going on in here? If we burn, even if you burn food, let's say you burn a marshmallow. Has everybody tried that? Well, imagine if we put a marshmallow inside here and lit it on fire. Okay, we would have this is a sealed vessel, and in fact it's sealed inside of a sealed container. Inside would be my burning marshmallow with an ignition wire, because how are you going to get it lit otherwise? And then that container is sealed, sitting inside, submerged inside a tank of water with a stirrer so that the water is mixed evenly, and a thermometer so we can measure temperature change. And of course, what's going to happen if this inner container is releasing heat, the water is absorbing it. Now, here's something we know and is important when we're doing the calculations for calories. It takes 1 calorie of energy to raise 1 gram of water 1 degree Celsius. So if we know the mass of the water inside the container, and if we know the temperature change of the water, we can figure out how many calories the water has absorbed. And the only place that it's getting that from would be, assuming the stirring is relatively slow, the only place the energy is coming from is that burning food in the inner container. Pretty interesting, huh? The calorimeter introduces to us a very important concept, the conservation of energy. You've heard that before, right? Energy cannot be created or destroyed. The calorimeter simply converts potential energy, that would be potential energy sitting inside the chemical bonds of that marshmallow, into heat energy when it actually is being burned. When this occurs, whether it occurs in one step, such as in combustion or burning, or in a series of steps, such as in digestion, when you maybe would consume that marshmallow, the overall amount of energy that's released is the same as long as the products are the same. And they are carbon dioxide and water. All right, so how do we measure temperature? And what are my little notes all around here? Well, you know how we measure temperature. We use a thermometer. Temperature is a measurement of how hot or cold an object is compared to something else. Heat, and here's where my notes up here, this is very important. Heat always flows from a hotter object to a colder object. So for instance, if you put an ice cube in your hand, you know what's going to happen, right? The ice cube's going to melt. Heat is being transferred or moving from your warm hand to the cold ice cube. What does temperature actually measure? Well, it measures the kinetic energy of molecules, and it's equal to the equation 1/2 mv squared. That's mass times velocity squared. Now, here's one interesting note here at the bottom. If you vigorously stir something, say a liquid, its temperature will slowly rise. Try that in your kitchen. Grab a thermometer, grab a glass, grab some water, and maybe a spoon. Measure the temperature before, and then start stirring it as fast as you can, and you will see that there's a temperature increase. Why is that happening? Well, you're transferring kinetic energy, moving that spoon and stirring it up from your hand and from the spoon into the energy into the molecules of water, getting them moving more, which means the temperature will be higher. Okay, temperature scales. Up here my notes, gas laws. You're not actually going to see Kelvin until we talk about gas laws, but since we're talking about temperature now, I'm going to introduce it. So the 3 temperature scales, we're all familiar with Fahrenheit, right? And I've introduced Celsius and Kelvin in the last lesson, but we're going to bring it up here and I'm going to show you how it converts. So Celsius is the SI unit of temperature, the essentially metric, the scientific unit, and it's what most people all over the world use, with the exception of course, the Americans. Okay, so how do we convert between the two? Well, I'll be honest, there's an equation. Of course there's equations. There's equations for everything. Converting between Celsius and Kelvin is pretty standard because if you would look at this example here, I have 3 beakers of boiling water and thermometers in each of them. I'm measuring, even though I've scribbled all over it, I've measured with the thermometer. There's a red line of alcohol inside these thermometers, and if I use it a Kelvin thermometer, I will see that the temperature is 373 Kelvin. If I use a Celsius, it's 100 degrees Kelvin. Now, if I were to look at the the freezing point of water, on the Kelvin thermometer, it'll be 273, and on the Celsius, it'll be 0. The difference between boiling and freezing on the Kelvin thermometer is 100. The difference between the two on the Celsius is also 100. That tells us that they're very close together, and in fact, the only difference between the two scales is 273 degrees Kelvin. Notice that, whether I'm at freezing water, 0 versus 273, or whether I'm at boiling, 100 versus 373, the difference is 273. So the equation for the conversion, Kelvin equals Celsius plus 273. That's what you'll use. Fahrenheit's another beast. Unfortunately, you will not see the 100 degrees difference between boiling and freezing on the Fahrenheit. No, instead it's 180. So let me go to the next slide and I'll show you how we can factor in and figure out a Fahrenheit temperature. Okay, so my little graph over here just shows the temperature for Fahrenheit. Boiling point is 212, freezing point is 32. The difference between the two, that's 180, right? Okay, question up here is, a person with hypothermia has a body temperature of 34.8 degrees Celsius. What is that in Fahrenheit? So we're going to use what we had on the last scale, or on the last slide, excuse me, to figure out an equation for converting Celsius to Fahrenheit, and then we're going to do it. Well, if you graph it and get the equation of the line, y equals mx plus b, remember, that's your equation of the line, where m is your slope, and slope is rise over run. As you go up 180, you go over 100 degrees, well, 180 divided by 100 is 1.8. And then you've got to add 32. So this right here, that is your equation for converting Fahrenheit to Celsius. You take your temperature in Celsius and you multiply by 1.8, and then you add 32 to all of that. Keep in mind your order of operations. So right here, doing my patient's temperature of 34.8, 34.8 times 1.8 plus 32. My temperature in Fahrenheit for this patient who has hypothermia is 94.6. And you can see, hypothermia, excuse me, you can see up here when patients are considered to be hypothermic and when they're considered to be hyperthermic. So hyper is too high, would have a fever, can result in death. Hypothermia is too cold, can also result in death. All right, here's some interesting things here. If you want to look at this table at some point, you can. I'm not going to read it all to you. It just has some different temperatures and in the 3 different scales. So the sun on average is at 9,937 degrees Fahrenheit, which is 5,503 Celsius, and that's 5,776 Kelvin. Holy cow, that's hot. You can compare that to a hot oven, the desert, a patient with a high fever. You can read through all this. But here's something important, and interesting probably more than anything at the bottom. Helium. Why do we care about helium up here on this? Why is that considered, you know, something that we don't see any other elements listed up here? Well, here's why. Magnetic resonance imaging. Do you know what that is? You want to be a nurse, don't you? Well, magnetic resonance imaging is also known as, anybody? MRI. MRI. So, if you have a patient who is being diagnosed, looked at through, assessed with an MRI, what's going on? A high field magnet aligns the nuclei in the body, typically the hydrogen in the body. Hydrogen is very prevalent in our body because hydrogen is in water. Water's H2O, and our body is almost all water. Our blood, for instance, full of water. To achieve these high fields, the magnets have to be cooled, however. They naturally want to be very, very hot. We've got to keep them very cool. In fact, they have to be so cold, they keep them cool with liquid helium and at liquid helium temperatures. Here's your interesting fact for this. Okay, so a few slides ago when we were looking at the calorimeter, I said that for water, it is 1 calorie per gram per degree Celsius. What in the world is that? Well, that's what's considered the specific heat of a substance. So a specific heat is the amount of heat that raises the temperature, so amount of energy, that raises the temperature of a fixed amount of a substance. Typically, it's a comparison of 1 gram for 1 degree Celsius. Different substances have different properties, and therefore they have different specific heats. And you can see down here all sorts of different common substances along with their specific heats in either calories or joules. So I already talked about it for water. But let me again emphasize what this means. So I don't know, let's pick something aluminum, such as like aluminum foil in your kitchen. It takes 0.214 calories of energy to raise 1 gram of aluminum by 1 degree Celsius. That's what this means. Or if I want to look at it in terms of joules, 0.897 joules of energy is what it takes to raise 1 gram of aluminum 1 degree Celsius. Huh, interesting, huh? All right, so let's look at this next question here, a couple of questions. When ocean water cools, so it's cooling down, the surrounding air does what? Do you know? If the temperature of the water is getting cooler, heat energy therefore is being released, the surrounding air gets warmer. Sand in the desert is hot in the day and cool in the night. What does that mean? Well, sand absorbs a lot of heat from the sun and then releases a lot of heat. Therefore, which do you think it is? Which do you think it is? Oh, I'm going to let you answer that one. Finally, last but not least, let's work through this one because this is really important. How many calories are needed to heat 100 grams of water from 25 degrees Celsius to boiling? Do you remember what boiling is for water? In Celsius, 100 degrees Celsius. Okay, so our equation for calculating this, calories needed will be equal to the amount of material, so that's a mass, typically in grams, times the specific heat, which is a constant, which would either be given to you or you come to get from like a table on the last slide, times how much temperature you're going to change. So if you start with hot water and you're going to take it to boiling, it actually will take less energy than if you're starting with cold water. Did you know that? Okay, so the amount of material, that's my mass, it's 100 grams. The specific heat of water is a constant, it's 1 calorie per gram per degree Celsius. And how much am I changing the temperature? Well, I'm going from 25 to 100, so final minus initial. I'm heating it up, so it's a positive 75 degrees Celsius. So the total calories needed will be 7,500. 7,500. Seems like a lot if you think about it. Okay, let's jump back now to something a little more simple. Classification of matter. So everything is matter, even the air that you're breathing right now. Made up of stuff that we'll talk about later, but it's stuff. It's not a vacuum of empty space. There are molecules in the air that you're breathing. Everything is matter. So matter can be classified as a pure substance or, we'll learn later, a mixture. We're going to focus on the pure substance part of it right now. Pure substances are broken down further, either an element, you know, those things on the periodic table of elements, or a compound. And compounds are composed of 2 or more elements. You can see my example here of copper and water. Here are some more examples of compounds. Compounds, hopefully you're given the chemical formula. And you can see that I have symbols for different elements, or more importantly, there's more than one element. It's considered a compound. Physical states, everybody should know this, right? Solids, liquids, and gases. Now, that's, hopefully you do know. What you may not know are the definitions in terms of their properties. Solids have a definite shape, they have a definite volume, okay, unless you do something to them. They're packed very close together in a fixed arrangement. Liquids have an indefinite shape, but a definite volume. So in other words, think about a glass of water. If it's in the glass, it takes the shape of a glass. If you pour it on the floor, it has the shape of your floor. That's what that means. Definite volume. So if you have a 1 liter container of water, that's 1 liter. Even if you pour it on the floor, it's still a liter. Your volume is unchanged. They take the shape of their container, like I was just talking about, and the particles are close together, but they're moving around. They're mobile. Finally, last but not least, we have gases. Gases have an indefinite shape, indefinite volume. You can change them, move them, do whatever you'd like. They have the same shape and volume as their container. They are far apart, and they move very, 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 very fast, almost as fast as I talk. Many materials exhibit all three phases or states of matter. For example, H2O. We know it as water when it's a liquid, ice when it's a solid, and steam or water vapor when it's a gas. Now, that's water. I'll be honest, most things don't have common nicknames like that for their different phases, but water does. Okay, let's look at what happens to the temperature of 1 gram of pure ice, that's solid, at 0 degrees as we continuously add some heat. Well, so we're going to start down here at 0 degrees Celsius, okay, and we've got ice and water as it starts to liquefy, and then we increase the temperature of water, then we're boiling it, and then it goes up to steam. So what actually is happening, I have a phase change and a phase change. And you probably didn't realize this, but just to change phase, not to change temperature, but to go from ice, which is solid, to water, which is a liquid, you're just changing phase, and that requires energy. And in fact, it's called the heat of fusion or heat of melting. That requires a certain amount of energy. Why is that? Well, because you're overcoming things we'll learn about later, these things called intermolecular forces, but you're putting distance between the particles when you go from a solid to a liquid. That requires energy. Okay, then we're going to go up the hill here, and we're going to change the temperature from 0 to 100. And of course, changing temperature, we learned about specific heat. Changing the temperature of a substance requires energy as well. And then, now let's go on to the next. Then right here, another physical change. We're going from liquid water to steam. Physical change, we're vaporizing the water, and that takes 540 calories per every 1 gram. These guys down here, by the way, are considered constants, and you'd have to be given those. So it takes energy again to change phase. To go from a liquid to a gas, you're putting even more distance between your particles, because remember from the last slide, gases are very far apart. And then last but not least, you're heating up the steam. So you're not just getting it to 100, you're going above 100 to wherever is up here. Again, changing phase is going to require energy, or not changing phase, sorry, changing temperature is going to require energy. That mass times specific heat times delta T, or change in temperature, that's the equation you'll use for that. Okay. Now, what happens if we have 1 gram of water at 100 degrees Celsius and we remove heat? Well, guess what? It cools off. And the exact opposite is true. Okay? The exact opposite is true. Instead of requiring energy, for instance, to phase change, we would be releasing, or you'd have a negative energy value. You'd be releasing energy as you did these things. Okay, sublimation. Have you ever seen dry ice, especially around Halloween? Looks like this. Sublimation occurs when a solid goes directly to a gas. It's very typical of dry ice, which sublimes at 78 degrees Celsius. And it takes place in frost-free refrigerators. It's used to prepare freeze-dried foods for long-term storage, or it's used at Halloween or on movie sets for special effects. How much energy do you think it would take to sublime 1 gram of ice freeze-drying at 0 degrees Celsius? Well, guess what you're going to need? You would need to go from solid directly to a gas. Okay, you would need both the heat of melting and heat of vaporization, because you would be melting it solid to a liquid and then vaporizing it liquid to a gas. The combined effect, going directly from a solid to a gas, is the combination of the two. 540 for the heat of vaporization, how much energy it takes to vaporize it, plus the 80 from the heat of melting. Here are some heats of fusion and heats of vaporization, again, for just common substances. These are constants. You would either be told to go look these up, or you would be given these on a problem. So the heat of fusion, the energy needed to disrupt the packing of molecules in the crystal. The structure of the molecules remains unchanged. So for instance, H2O is a solid as ice melting into a liquid. It's still H2O. The structure of the molecule remains unchanged, but you're disrupting how they're packaged. You're changing the phase. You're putting distance between the particles, and that requires energy. The heat of vaporization is the energy needed to disrupt the interaction between the molecules in the liquid. Going from a liquid to a gas is heat of vaporization. The origin of these interactions, again, as I told you, we will talk about later. But again, like the last one, the structure of the molecules remains unchanged. You still have water in my example. All right, some physical properties of substances. Here are some things just for copper. I'll let you look at that if you want to look at that. There are properties known for all sorts of common substances. Copper is one very common substance. You probably already know some of these, the color, the odor, it's odorless, it's shiny, it's a solid. Maybe you know it's good for conducting electricity and heat. The melting and boiling points, they're very, very high, as is typical for most solids. All right, some examples of physical changes. Changing state, talking about boiling or freezing. Changing appearance, that's still just a physical change. Physical change, you have not changed what you have. Water is still water, it's still H2O. It might be ice or steam, but it's still H2O. You can dissolve sugar into water. That's actually just a physical change. Nothing chemically is happening. Changing the shape or changing the size by cutting something, drawing something, hammering it, whatever it is, you still have the same substance, you just have it in a different shape. These are all physical changes. Chemical properties describe how something would react chemically, and chemical changes when you're changing what you have. So the properties describe how a substance will change into a new substance, or chemical properties describe chemical changes. And a chemical change we also know as a chemical reaction. You start with one substance, such as iron, and you end up with something else, such as iron 3 oxide. All right, here's an example of chemical changes. There are lots of chemical changes. Combustion is another one. A piece of metal rusting, that was on the last slide. Something that tarnishes, like when silver tarnishes. Lots and lots of chemical changes, and we're going to look this whole class at chemical changes and reactions. Okay, let's see in this last one here. Can we classify each of the following as a physical change or a chemical change? All right, when you burn something, burning anything is chemical. That's combustion. Melting, I don't care what is melting. Melting just means going from a solid to a liquid. That's physical. Toasting a marshmallow, well, I don't know if you've ever done it like I have, but I'm kind of burning the sugar on the outside of the marshmallow. Toasting a marshmallow happens to be chemical. Cutting a pizza, remember cutting, just changing shape? All we're doing is a physical change. And polishing a silver bowl. Now, some of these get a little tricky. But if tarnishing is chemical, I'm guessing the opposite, making something shiny again, that's probably chemical as well. So these are pretty tricky. These can be pretty tricky. I'm always looking for keywords. Burning, combustion, things like that would be chemical. Melting, freezing, boiling, physical changes, cutting, changing size, those would be physical changes. Okay, that's all I have for you in this lesson.